Today we're going to learn about static electricity. First of all, an electric charge is caused by the charged particles inside an atom. Specifically, the protons have a positive charge and they are stuck in the middle of the atom. They are bound tightly in the nucleus. Electrons have a negative charge and they are free to move around the nucleus in orbitals. If a substance is a conductor, it's a metal like aluminum, gold, silver, copper that has loosely bound electrons that are free to move from atom to atom. An insulator holds more tightly to its electrons and does not let them move about. Therefore, they do not conduct electricity. Charges were actually given the name positive and negative by Ben Franklin. Opposite charges will attract and like charges will repel. So two positives will repel, two negatives will repel, and a positive and a negative will attract. Now, in magnetism, you've always got to have a north pole and a south pole. You can never have just one of them alone on a magnet. They always come together. However, with electricity, electrical charges can exist alone. You can have just a negative without the positive. Yes, the positive will be somewhere in the world, but it doesn't have to be right there with the negative. Electric charges cause an electric field by exerting a force through the force field in all directions out from the charged particle. Here, for example, is a positively charged particle exerting a force outward, and here is a negatively charged particle exerting a force inward. When two charged particles get beside each other, they either attract or repel. Here is an example of a negative and a positive attracting. See how instead of the lines going straight out, they curve and attract to each other. That's what happens when the opposites attract. When two like charges repel, see how instead of going straight out, the force field lines turn away and never quite touch each other. And that is what happens when like charges repel. Please draw this sketch right here. Just like in magnets, as you get closer to the magnet, the magnetic field increases the closer you get to the magnet. With electric charges, the electric force field increases as you get closer to the charges. Notice how, when you get close, the lines are close together, indicating a strong field. Then, when you get further away, the lines get further apart, indicating a weaker field. The further out you go, the further apart those lines will go, and the weaker the electric field becomes. So the word static comes from the Latin word stasis, which means stays. Static electricity is staying electricity. It doesn't move, it just builds up and stays where it is. See, objects are typically neutral. That means their positive protons and their negative electrons are equal. An atom or an object can become charged by gaining or losing electrons, not protons. The protons are trapped in the nucleus. They must stay still. The electrons are on the outside in those orbitals and they can move around and move from atom to atom. The buildup of these electrons is called static electricity. In static electricity, the charges build up and stay. They don't flow. If they flow, that's called current electricity. It's a current of charge that is flowing. There are three ways to transfer static charge. The first is friction. By rubbing my hair against this balloon, I transfer negative charges from my hair to the balloon. The electrons are more attracted to the balloon than they are to my hair. Have you ever walked across a rug and then touched the metal doorknob and get shocked? Well, you built up the static electricity, and when you touched that doorknob, you had current electricity. You had static discharge. The charge moved out of your hand and into the doorknob, and you got shocked. The next way to transfer static charge is by conduction. In conduction, two objects must make direct contact with each other. This is a Van de Graaff generator, and it builds up up static electricity because there's a belt inside running that brushes against a little metal brush and builds up the electrical charges. So I'm going to place my hands on the Van de Graaff generator, and I cannot let them go because then I could be shocked. All right, please turn on the Van de Graaff generator, my assistant, Mr. Lowe. And now it is building up a static charge, and through conduction, well, it's building up the charge through friction. Then through conduction, the electrons are moving to me. You'll see how my hair's starting to stand up a little bit. That's because each hair has some negative electrons on it. And since all the hairs are negative, they're all repelled from each other and pushed away from each other. So there's the buildup of the static charge. Now we're going to have static discharge, a type of conduction. And Mr. Lowe is going to touch a metal wand to this Van de Graaff generator and discharge the static electricity that is built up. Go right ahead. It startled me. It doesn't shock you, but it startles you. It feels like this wind goes whooshing up my hands. So you'll see my hair's falling back down again because it has discharged the static. Now he's going to remove that ball, head, and you'll see it builds up the charge again, and my hair has gotten the static electricity. All right, now he's going to discharge the Van de Graaff generator one more time. There we go, didn't jump nearly so badly. And now he can reach down and turn it off safely, and I won't get shocked. So, for example, when you touch a Van de Graaff machine, that will transfer the negative charges to you, and they build up. So that's by conduction. The third way to transfer static charge is by induction. Induction is what happens when two non-conducting objects charge each other. You've heard of a woman being induced into labor to have her baby, right? Well, inducing means caused to have her baby. So induction means causing. What happens is a charged object causes a charge in another object. Let's look at this. Here we have a balloon that has built up a negative charge, probably from being rubbed against somebody's hair. And here's a wall that is not charged that has equal number of positive protons and negative electrons. Remember, the electrons can move and the protons cannot. When the balloon gets up close to the wall, the positive protons stay where they were. The negative electrons are repelled from the negative balloon and they are pushed deeper into the wall. Now the wall has a charge. This deep inside is negative and on the surface is positive. So when you get that negative balloon beside the positive wall, the balloon will actually stick to the wall. Isn't that cool? Friction has now caused this balloon to be negative. When I place it against the wall, it now sticks to the wall. Now you'll notice that once you put that balloon on the wall, the charges don't stay forever. Eventually the balloon will fall off the wall. So what happens? Well, objects tend toward equilibrium. They want to be neutral. They want to have equal numbers of positive and negative protons and electrons. And so when electrons move towards this equilibrium and even back out, that's static discharge. In the case of the balloon, it's very, very slow because the electrons are attracted to the water molecules that are in the air. So a humid day, the balloon will fall off the wall fairly quickly. But on a dry day, the balloon can stay up for several hours before the water vapor in the air finally draws off the electrons. On the other hand, if you scuff your feet on the floor and then touch the doorknob, well, that is very fast static discharge, and you feel the shock because of the moving current. Like we have said, humidity or water vapor pulls electrons off of negatively charged objects, preventing the static charges from building up. So when you scuff your feet across a carpet, friction between your shoes and the carpet pulls the electrons off of you and puts them into the carpet. You have leftover positive charge, so you are positively charged because you have lost electrons. You have not gained positive, you have lost negative. Then you touch the doorknob. Well, the electrons in the doorknob want to equal out between you with a lack of electrons and the doorknob with a normal amount of electrons. So you touch the doorknob, the electrons jump into you and shock you. If you were negative and the doorknob was positive, you'd feel the same thing. You couldn't tell which way the electrons were going because it would shock you either way. In a thundercloud, the bottom of the cloud becomes negatively charged and the upper parts of the cloud become positively charged. Then the lightning is a giant spark of those negative electrons jumping to the ground or within the cloud to equal out the electrical charge. And when that giant spark jumps, that's lightning. If you want to detect electric charges, you use an electroscope. It's a metal rod stuck into a glass container. So there's a metal circle here, sometimes a metal ball, a metal rod, and there are two pieces of metal foil. Aluminum foil works, gold foil is even better, but of course that's way more expensive. When there is no charge, the aluminum foil or gold foil or whatever, the metal foil hangs straight down. It's not attracted to the other foil, it's not repelled. But if you bring a charged rod close to it, don't touch it, but just get close to it, it will push the electrons away. And notice how now that the two pieces of foil are both negative, they are repelled from each other. Now, which one is that? Friction, conduction, or induction? Well, notice it pushed the electrons away and caused a charge without actually touching it. Therefore, this is induction. If you did this with a positive rod, then the negative electrons would be pulled upward towards the positive rod, leaving the bottom part positive. The fact that both pieces of foil are positive makes them repel each other and stick out. This is also why when you touch a Van de Graaff generator, your hair will stick out, because you build up electrons on you, and each piece of hair has electrons, and all the electrons repel each other. So that's why your hair stands out. Once you remove the negative wand from the electroscope without touching it, these charges mix back together and become neutral again. However, if you actually touch the electroscope with the rod, the negative electrons will be split between the rod and the electroscope, charging the electroscope. Then the electroscope will have a charge that will remain on there until it slowly dissipates. Remember, only the negative charges flow. The positive charges stay put.